then I will. Right, so I promised but did not do it. So to prove Theorem 1, demonstrating some middle school techniques, so I'll do it now. Because I really like the proof. So Theorem 1 says that if Aij is n by n complex matrix such that all entries are within distance 1/2 from 1, then the permanent is not 0. Right. So, and here's a proof. We prove it by induction on n, but we prove a stronger statement. So, induction on n. What do we prove? We prove that if Aij and Bij are two n by n matrix like that one. Matrices as above. That's with the entries within 0.5 from 1. And they differ just in one row or one column at most. Then not only the permanents are not 0, but if we think of the permanents, the complex numbers as vectors in the plane, then the angle between them doesn't exceed pi/2. Right. So for n equal 1, that should be pretty clear because what do we have here? We have just 1 by 1 matrix, and that's 0, that's 1. We pick complex numbers from this disk, and of course the angle doesn't exceed pi/2. It actually doesn't exceed pi/3, right? So the induction step, how do we go from n minus 1 to n? So pick two matrices like this, and assume that they differ in the first row. Right. So what we can do, we can expand the permanent using the first row. So the permanent of A is the, just Laplace expansion, the sum of A1j, the permanent of the minor, right? So the submatrix that you get by crossing out the first row in J's column. And the same is true for the permanent of B. You get B1j, but the minors will be the same, right? Because it's only the first row that differ. Now what we do, we look at any two minors and we notice exactly what? That they differ in at most one column. Right, so AJ1, AJ2 differ and at most one column. So therefore, by the induction hypothesis, so the permanents are not 0, and the angle between any two doesn't exceed pi/2. So the rest is, as promised, middle school exercise. So lemma, which has nothing to do with permanence or anything at all, but plane geometry, so that if you have a non-zero complex numbers, where the angle between any two not exceeding pi/2, and if you have a collection of numbers, complex numbers, say alpha j, beta j, that are within distance 0.5 from 1, then for the linear combinations with those numbers, we have that the linear combinations are not 0, and the angle does not exceed pi/2. And that's a proof. So I kind of like it, so it doesn't use anything. My previous, so it's not the first proof I came up with, so my previous proofs used mathematics, and they've given me weaker constants. So the more mathematics I used, the weaker constants I was getting. So that's where I stopped at 0.5. I cannot prove it. So 0.5 is optimal for this particular proof, but it's certainly not clear at all if it's optimal for any as a constant. Right. So again, any objections to the proof? So, and you have as an exercise, homework exercise, to prove a similar result for complex matrices where you give more leeway for the real part, but pinch the imaginary part. It pretty much goes the same way. Okay. So, right. Yeah, I like it. So I'm kind of proud. I haven't found it then. So, okay, so I'm going to move slowly in the direction sort of a more murky waters, like as we will have this part on open problems. So the next thing I'd like to talk about is the chromatic polynomial, right? So, and for which we did the exercise. So let's recall what it said. Right, so chromatic polynomial. So given a graph with no loops, no multiple edges, so we have a proper Q coloring. If the endpoints of every edge are colored differently. right? If for every edge in the graph. And so we introduce that number of proper colorings, chi of q, to the number of proper q colorings. And over the in-class homework session, we proved that it's indeed polynomial. So we proved that interesting representation. So proved that. So I can keep the graph. So proved that it can be written as the sum of all collections of edges, including the empty collection. That's perfectly all right. So q to the number of connected components of the graph induced on the same set of vertices with those edges, and -1 to the number of the edges in the collection, right? So there C prime is the number of connected components of the graph with the same set of vertices. So isolated vertices still count as connected components and the subset. So we did it, right? So that, of course, allows us to define it for any complex number. Just by the very same formula, basically by renaming q. So, this provides a marvelous example of interpolating from infinity. So, interpolation from infinity. So it was observed by Hus Rex, who is here, and then observed again on the sort of deeper level by Hus and Naresh Patel. What did they observe? They observed that a conjecture by Sokal which says that this polynomial is not zero, provided the real part is greater than the largest degree. On the graph implies, for example, that the number of like delta plus 1 proper colorings can be approximated in polynomial time within any error epsilon, provided delta fixed is in advance. Right. So, so people tell me that experimentally, Sokal conjecture looks very plausible, right? So, yeah. So we still don't know how to prove it. So what we do know, though, is there is a Sokal theorem. So which says that this polynomial has no zeros if the absolute value of the argument is greater than some constant, like Sokal proof 7.9 times the largest degree, improved later to 6.9, and I think, was it improved afterwards?
No,
right. So basically, what does it say? So what we know for sure is that there are no zeros in a sufficiently large disk. Large, but proportional only to the. No, I'm sorry. There are zeros here. Like no zeros outside. Yeah, no zeros outside. No zeros outside. And we also Sokal conjectures that there are no zeros in that half plane. Right. So then, as Hughes noticed, that can be used to interpolate very quickly. Namely, we interpolate not from 0 like we did last time, but coming from infinity. That makes a perfect intuitive sense because it's much easier to color graphs properly if you can use infinitely many colors. Basically, just color at random, so that will do. Right, and then you can kind of crawl, knowing that there are no zeros in the vicinity. So what you do, what they did, so you introduce an auxiliary polynomial. So you revert the coefficients. So z to the v, there v is the set of vertices, times the chromatic polynomial computed at the point 1 over z. And if we use this expansion, so what do we get? So we get, so it's the sum over all collections of edges, right? Including the empty collection, but this time we get z to the cardinality of the number of vertices minus the number of connected components, right? Times the same -1 to. So we have that. So then, what does Sokal conjecture translate into? So Sokal conjecture translates into the fact that, so if we use the inversion, right, then this half plane translates into a circle, disk rather, and this is somewhere 1 over delta, right? So no zeros here. No zeros for that polynomial, right? Sokal theorem. Translates into the fact that maybe I should have used a different color. How about, yeah, I write Sokal conjecture in green and the picture in green. So Sokal conjecture so it says that there are no zeros in the disk. So Sokal theorem says that there are no zeros in the small disk around the origin. So Sokal theorem says that there are no zeros here. Right? And we are up to interpolation, right? So we got a strip, a zero-free strip from 0 to 1 over delta plus 1. So got a 0 free strip, right? So we can interpolate to 1 over delta plus 1, provided we can compute the first logarithmically many derivatives, right? So can interpolate this polynomial P of Z, provided the derivatives at 0 are sort of accessible, so that the first few derivatives can be computed easily. But when we look at the derivatives, right, so the case derivative is what? Up to the, of course, k factorial, right? So what it is, so we just collect the sum over all a collection of edges, of which there are very few, so that the number of connected components that we get is equal to k. So if k is small, then that basically implies that there are many connected components, just every vertex is a connected component except maybe some small number of k, which means that there are very few edges we're talking about, right? So -1 to the prime. So, and that, as Elric noticed, so for logarithmic k, it can be computed in polynomial time. So it can be computed in some 2 to the of k time. Right. And therefore, we are set to do interpolation. So we know logarithmically many derivatives. We find them very quickly. And we have a 0 free strip. And we just go there. Right. Yeah. And that's, as I understand, the resultant count in delta plus 1, right, is still open, right? So the best is 11 over 6 times delta, right? 11 over 6 minus epsilon, right, times delta by Markov chains, right?
I mean, maybe it's worth saying that the method that Sokol used to prove the theorem also gives the algorithm directly.
So he used, he used this cluster expansion, which
he shows that a power series for log partition function converges exponentially fast and is supported on connected objects.
Right. Well, yes, but you can always. Well, okay.
Yeah. It's just direct from the proof.
Yeah. Okay. Okay, but yeah, right. But still, to do this whole, that's it's not quite enough, right? So we need the Sokol conjecture, bigger one, right?
Yeah, I'm saying the Sokol theorem to algorithm.
Right. Okay. Right. Okay.
Yeah, not the conjecture.
Okay. Right. So that's an example of things where things stand. So they kind of open. Right. We really don't have much clue.
So is it known for some special cases, like is it easy to prove for trees or something?
That I don't know, but probably, yeah. Or series parallel graphs or something like this. Yeah. So the problem, if you, as I see it, so the problem is that when we want to prove something like this, then we can prove it by induction. We don't know anything else. And for the induction, we ought to have a whole family of objects somehow related by in various ways. And here there is only this chromatic polynomial and nothing around it. But I'm going to talk about some sort of trying to make this problem sort of more amenable, kind of inductive argument, and maybe proof. So, but before that, so again, any objections? Right. So, okay. So what we'll do, we'll try to consider a more sort of a broad notion, hoping to get something out of it, simply because it just allows us more flexibility. So, and that will be the graph homomorphism partition functions. Okay. So, graph homomorphism. Partition function. Right. So, what is this? So we still have a graph with the same usual assumptions that no loops, no multiple edges. We have a symmetric matrix. So denote the size q by q, so that to allude to the coloring question. So symmetric, possibly complex. Right, and what we do, we introduce a polynomial, associate a polynomial with the graph. So it's the sum over all maps of the set of vertices to the set Y to Q. And then what we do, they take the product over all edges of whatever matrix entries we got. So with every graph and every Q, therefore, we associated a polynomial. And the interesting thing that it encodes an awful lot of things. So for example, how does it relate to the chromatic polynomial? So if your matrix has just zeros on the diagonal, right, and ones off the diagonal, then the value is just the number of proper Q colorings. Right. So on the other hand, if even for like 2 by 2 matrix, so if A has this structure, 0 in the corner, 1's outside, then the value is the number of independent sets. So why is that? Because so an independent set will be the inverse image of 1, right? Because we don't want to, the moment we get two endpoints mapped to 1, we pick up 0 and the term disappears, right? So therefore we just counting, so with every such a map we associate the inverse image of 1, and that gives us an independent set, and vice versa. So the nice thing about this object is that we got more flexibility. We have like many variables. So that's something to use, right? So, okay, so that's the object. So any, again, objections to the object? By the way, when did I start? Where do I finish? So I finish at 10, right? After 12.
Finish at 12, 10, yes.
Right. Okay, good. So, so with Pablo Sabaron, we proved zero freeness result for this thing. And actually, to do induction, so the proof was very much similar to the one I showed you for the permanent, right? So it's the same idea. So you embed it in a bunch of related objects. So what we did, we actually considered a more general object, because it looks like that the more general object you have, the easier to induct, right? So it's not a new observation. So even more general. So assign a separate matrix. Matrix A, use V to each edge. So what we get then, we get this object. I'll still denote this collection of matrices now by A. So it's the sum, again, overall numbering sort of, or colorings, if you wish, or spins of vertices. And the product now picks up the entry of the corresponding matrix. And the advantage of that is that we get a really multi-affine thing, which is easier to deal with. So what we proved, so we proved zero freeness. So with Pablo Sabaron. So if the entries are within a certain distance that inversely proportional to the largest degree, of the graph, then this functional is not zero. So again, so it's non-zero in the polydisk. So later I sort of simplified the proof and kind of made the bound better. So what it looks now, it says that let delta sub delta, that's a nice notation, right? So especially when you kind of articulate it, the maximum of the function I'll just write it. Will not say what it is. So sine alpha over 2, so cosine alpha delta over 2. So then this homomorphism partition function is not 0, provided, again, the entries are within that distance to 1. Right, so in particular, we get a reasonable value. So the first interesting case when the degree is 3, right? So we get like 0.18 roughly. So d4 is 0.13 and so forth. And generally, we have that bound. And so the proof, as I said, so it's basically the same proof as for the permanent, only with bells and whistles. So instead of a permanent or submatrix, you have a graph homomorphism partition function with additional constraints that it maps some chosen vertices to some chosen indices. Right. But it's the same sort of induction and looking at the properties of the vectors in the Euclidean plane. Right. So later, that's let's call it a disk theorem. So later, I proved a strip theorem that if you just care about real matrices, then you can get a better bound. So what it looks like, this is one disk that we proved the existence. And so the picture is the same as Alistair had yesterday. So the strip is longer. So strip theorem basically allows you to choose this delta 3 if you pinch the imaginary part. So delta 3 will be tangent of pi over 9, which is approximately 0.36. So you can go from 1 both ways by 0.36 if the degree of if the largest degree of the vertex is 3. And general formula for larger is tangent of pi over 4 times delta minus 1 for delta greater than 3. Right. Right. But as you approach these numbers, so the strip becomes thinner and thinner. So no zeros here. So and then you apply interpolation, and you say that if delta is and plus, of course, idea is to compute if you just imply, as they say, vanilla interpolation, you get quasi-polynomial algorithm. So interpolation gives you quasi-polynomial algorithm. Approximation algorithm. And if we add here the sorcery of Patel and Rags, then in those domains, the slightly small domains, so we get polynomial time algorithms, approximation algorithms. If the largest degree is fixed. Okay, so that's sufficiently general object. So what I do suggest that we stare at it for 15 seconds, right? Let's see if there are any issues here.
you say more what is the observation of Elric?
Yeah, so the observation for Elric, so when you do it like I did for the permanent, right? So you'll be summing up some polynomials over collection of edges of logarithmic size. And in principle, so if you just do it naively, as I do, so that gives you quasi-polynomial, right, n to the log n. But what they noticed, and for me it's kind of nothing short of kind of sorcery, that somehow you can only restrict yourself onto collection of edges that are connected. And then it becomes polynomial in a fixed degree, right?
Things decompose as products?
Well, I guess, so that's what Alistair talked about yesterday. So they decompose. So not quite as products. So it's more like relations between Newton sums and between the moments and elementary symmetric functions, or between, if you wish, between cumulants and moments. Right. So. Right. So there are two remarks I'd like to make. Maybe I finally raise this sort of the slogan here, so what I'm talking about. So one remark is how what is it good for? First remark. So. What is it good for? I'll use red for that. So during this week, I've been bothering people asking, like, what are your applications? So, and I'm sort of previewing your question here. So, what is it good for?
Makes a living, right?
Huh? It makes a living, yeah, that's a very general question. So far, by the way, so I'm not so sure about the nearest future, the way things go. All right, let's not get into that. So suppose we want to solve some NP hard problem. So suppose we want to decide, is there a Q color, proper coloring of the graph? So Q proper coloring. So for some nasty Q, right? So if, I don't know, for Q equal 3, right? Say 4, 3. For some Q and delta, which makes it hard, right? So what we can do, we can attempt to, let's compute the graph homomorphism partition function on the matrix, which instead of ones on the diagonal has 1 plus delta so whatever delta I can afford by this theorem, and on the diagonal 1 minus delta, right? So what I'm doing now, so I'm considering all colorings, proper or not, but they're weighted exponentially. So proper coloring comes with weight 1 plus delta to the number of edges, I guess, right? And improper weighted down exponentially by in the number of miscolored edges. Right. So what does it buy me? It buys me something like that. So if I look at this number that I'm getting, and if it's small, right, then you can probably say that it's kind of far from being properly colorable. So whatever colorings I take, it will have sufficiently many miscolored edges, right? If it's large, well, then maybe, just maybe, right, there are sufficiently many proper colorings, even if the proper coloring can be sort of exponentially rare if you just try to color at random. So they do some sort of a version of the property testing, right? So they allow you to separate graphs that are far from being properly colorable, meaning that whatever coloring you take, there will be sufficiently many improperly colored edges, from the graphs that have sufficiently many proper colorings. Right? So if you have two graphs, you compare, then this thing will tell you the difference. And it's still better than nothing, I think, right? So it's still better than to say that the problem is sharply hard, I refuse to deal with it. Right. So, well, you do something. Right.
So this is the Potts model partition function.
Right. So it covers, right, Potts model.
I mean, this very particular one.
Oh, this, yes. Right. This is Potts model. Right. So what I also like to mention is that notice that the bounds do not depend on the size of the matrix, which means that you can take a limit and consider spin systems with continuous spins, right? And that's what you get. You get into, even for me, even murkier area of quantum Ising models and the like. But Will probably can shed a light on that. But so what's this model? What's the name of that model where you allow like spins on a circle and a sphere? Heisenberg. Okay, right. So it covers that, right? Because the bounds are independent on the size of the matrix, so you can take limits. Right? So other concerns or objections? So very recently, objections, no concerns. Yeah, very recently, there was a recent paper by Hughes, Davis, Patel, and Bench, right? So it's a very recent result. So when they wanted to go all the way, so here I stay around 1, they wanted to go to 0, but at the cost of making Q large enough, and also with the view towards the Sokal conjecture. So what do I do? I'll probably erase this. So that's an archive. That's Davis Patel. So what they consider a very special matrix. So A is of the type So 1 orthodiagonal. So we're still coloring. Complex number z on the diagonal. But Q is large, so they proved the existence of the strip all the way from 0 to 1, so the zero freeness. And as a corollary by interpolation argument, so the polynomial time approximation algorithm. Provided, so zero freeness in the strip. So that's where z varies. Provided Q is sufficiently large, is approximately 3.2 delta. And here's telling me that it's actually E. Right. So actually, actually E times delta. And there is still hope that you can put any number greater than 1, and that would do a proper coloring. So the proof is a bit more convoluted version of the proof for the permanent, but you would probably agree that it's some inspired the permanent of this middle school computation. So, but it's much more involved. Right. So, and as I understand, so it may well be that this E can be replaced by 1 plus epsilon. We don't know. If it's true, it looks easier than Sokal conjecture. Yeah. So maybe. Just maybe, we can have Q is greater than 1 plus epsilon times delta. Right. And if we do, then the interpolation does coloring. Okay, so I think my time is up, right? Is that right? Yeah. Okay. Jolly good. So again, any reaction of any kind?
So that Sokal theorem, can you prove it using this induction?
Sokal theorem using this induction, well, I can take Peter's Chikwari proof from his paper, which kind of goes by induction, but not this type, right? But it's inductive argument, right? From yeah.
So
that's how I learned it, anyhow. So from Peter's paper.
but it is practically the same as the original Sokal proof. Only here and there I just simplified some.
Well, which makes a difference, honestly, when you read it. There's little simplifications here and there. But it's essentially inductive argument, right? If you look at the Katetsky price, right? So it's still inductive argument, right? So it's probably fair to say that all these things are proven by induction, right?
I don't think Katetsky price is actually inductive. I look back at it, it's some strange thing about letting real parameters go from 0.
But it isn't the same as this bound, many people, Shearer, Sokal, Scott, Dobrushin bound. It's essentially the same bound, right? And that bound is inductive bound, right? Yeah.
Yes, but the trick is that first we encode the chromatic polynomial as a weighted independent.
Right, like we did, right? Yeah.
Do the
Right.
general.
But in hidden in that the Scott Sokal Shearer thing is that So on the real line is inductive, but then to go from the real line to the complex circle, you have to do Vivanti-Pingsheim, which is...
You should do, I'm sorry, what?
You sure the real line is the worst case?
Yes.
And that requires, maybe you can call that another induction, but that requires another argument that it has, the power series has...
It converges, right?
Alternating terms.
Oh, that.
You don't need that.
I don't think I'm sorry, I don't think well, there are experts here, but I think I can do it without, right? Without that. Without sign alternation, probably. Just strictly by induction. I think I did it actually in my book. Well, of course I didn't do it. I just lifted it off somebody. But
The real line, yes, but...
no, on the complex, right. So reals are not interesting. So off to quaternions.
Okay.